The natural environment includes hills, rivers, and beaches. Features in the built environment include buildings, roads, and drains. So when we represent all these on the map, it creates a common language that developers, architects, and contractors can all understand and build upon. So engineering surveying is basically any survey work that's carried out in connection with construction and building. So they use traditional survey methods such as what we went through just now, but digital technology and GNSS are increasingly being used. So there's an Institute of Civil Engineering Surveyors, ICES, and it basically gives the responsibilities on what it takes to be an engineering surveyor. It covers the positions of bridge, tunnels, roads, and other structures, producing up-to-date maps and plans, and setting out a scale at the right place, and as well as monitoring. So we'll go through that in detail later. I think why this matters is that when you graduate, you should be able to challenge a setup, interpret some coordinates, question the surveyor's tolerances, and basically make design decisions from the measured data. So above are some examples of where engineering surveys might be carried out in the construction of a major dam, construction of a highway, tunnels, and airports. So in parts of engineering survey, actually, there's a portion in hydrographic surveying. So hydrographic surveying actually processes the survey levels in the marine environment. So you'll encounter things like seabeds and riverbeds. And surveyors here actually specialize in positioning, depth measurement, and collecting data in marine environments. So in Singapore, this typically supports reclamation work, coastal protection work, and outlet drain works. As Hocklim Engineering, we carry out hydro survey as well in the canals to monitor silt levels to determine when is it appropriate to start dredging works. And this actually helps to maintain drain capacity in our drainage system, especially during the flash floods. Hydrographic surveying actually applies the same principles as land surveying. It's just everything that's under the water. So photogrammetry and remote sensing. These use images and scanning to create digital terrain models. Things like drones, LiDARs, and 3D scanners allow us to survey inaccessible areas safely and quickly. So in our company, we basically use photogrammetry to scan slopes, detect some kind of a surface movement after rainfall. And this kind of technology saves time and gives us a very accurate terrain data, which is very critical for slope stability analysis. Geographic information systems. So these geographic information systems basically help us to store, analyze, and visualize the data. GIS combines mapping with database intelligence. Agencies in Singapore, they're actually integrating GIS with BIM to build digital twins for planning and maintenance works. And in our company, we use GIS dashboards to monitor slope stability and drainage performance. It's actually a very powerful technology for turning raw survey data into something actionable. So a little bit about how engineering surveys are carried out. They typically follow 4 stages. Control survey. This establishes the permanent reference points. Mapping to collect detailed data. Setting out to translate whatever you design to the site. And monitoring, and that is during the construction and even the post-construction stage. So every stage actually builds on the previous one, and it's important to understand how do errors contribute to the accuracy, because if you get an error wrong, and then it just multiplies downstream. So precision basically starts from your very first benchmark. So a control survey creates the backbone of positional accuracy. So we talk about small sites and large sites. So for small sites, we assume a flat surface and we use things called a plane surveying. So when you survey in Singapore, we have already regularized it into a plane, and we call it the SVY21 coordinate system. But in overseas, when you have a very large scale or a very large site, you have to account for the curvature of the earth, and this is called the geodetic surveying. So at Hocklim, our first step to any project is establishing control points tied to the SLA benchmarks. We can get this from the SLA website in this. And it's important because without control, every subsequent operation, be it leveling, setting out, or monitoring, risks compounding these errors and bringing it forward. Well, the next stage is mapping. So we use mapping to carry out a detailed survey around the site, previously using the control points for reference and establishing a topography of the site. So this will include different features that you see, such as the hills, the rivers, like in the picture on the left. And this detailed survey is typically carried out using total stations or GNSS methods. And you need to do it digitally to get a map that you see on the right, which is a digital terrain model. Once you get this digital terrain model, actually it's pretty powerful. You can use this to identify, for example, in our recent projects, identify drainage bottlenecks. You can carry out a lot of redesign work. And mapping actually turns your field data into meaningful engineering design inputs. So I think this is quite a crucial part of the engineering survey. Of course, you have setting out. So setting out basically converts design drawings into the ground. So you can see in the pictures below where there are a lot of spray paints on the ground in various shapes and various marks such as the 178 you see on the picture on the right. This basically establishes the points, the positions, and the levels of whatever that is important to be constructed. And surveyors mark physical points on the construction site. It can range from pile caps to the center median of the road, the edge of the drain. And it's very important at this stage that you be as accurate as you can, because accuracy here basically determines the construction quality. And I would like to add that at Hocklim, basically the surveyors communicate constantly with the site supervisors, and you need to maintain your engineering survey tolerances. And setting out is where your design actually gets translated onto the ground. So this is the part where you get all your irregularities and you start to resolve the conflicts. So after construction, monitoring ensures that the structure or terrain remains stable during the construction. You will see very common monitoring tools such as ground settlement markers actually monitor the deformation or settlement of the surrounding structures during construction. So it's important to track displacement, settlement, and deformation as a civil engineer, because you want to know that the work that you do has minimal impact to the surrounding structures, especially in an urban built-up area like Singapore. So you can't carry out survey without surveying equipment, and this is the next section that we'll be going through. So this is a section on modern survey equipment. I think we can balance it against a traditional survey equipment such as theodolites, levels, measurement tapes. And these are still used very commonly in today's construction sites. But right now, there's been a big shift to knowledge about total stations, digital levels, laser levels, and these are much more productive. They're much more productive, and if you know how to use them, your ability as a civil engineer can be multiplied. So each tool actually addresses a different need. We generally group them according to degree of accuracy. For example, if you use a digital level, you want it for checking the heights and the levels, but you can't use it to calculate bearing. And laser levels we frequently use. You can see the renovation contractors using it to get their 90 degrees and their plumb and level to make sure that everything that they construct is straight and on point. So knowing which ones to use at different environments and different situations is actually part of the engineering judgment. So total stations, they can measure angle, distance, and with the amount of computing power that they put into some total stations today, you actually have many other functions. So it measures with millimeter precision and can store thousands of points. Not only that, when you combine it with laptops and other controllers, you can actually store and edit data on site, and you can actually do more information processing on site. So at Hocklim, we rely a lot on total stations for things like drainage alignment, encroachment surveys, and slope monitoring. You will be seeing the total stations during your lab sessions, and understanding how they work actually gives you a very big edge as a civil engineer when you join the workforce. So level and leveling stuff. So these measure vertical differences. One is the optics, and actually the other is a staff. So you use the level and the staff to measure things like drain gradients, to reduce levels. This is actually a very basic skill, and we'll be covering it in our first lab session. And precision leveling basically ensures things from like water gradient flowing well, and it can help to prevent future ponding issues after construction. So an updated version of the level is the digital and laser levels. So digital levels basically read bar-coded stuff automatically. This actually reduces the human error, which you will also learn about in the later part of the lecture. And laser levels actually project the reference plates. So these are very good for formwork and for road works when you want to understand gradient and surface runoff controls. So if you use a great laser during road paving, you actually set a correct slope for your runoff into the nearby water catchment areas. These instruments typically increase the efficiency, consistency, and the safety on site. Okay, GNSS is it's called the Global Navigation Satellite System, and it's been quite a breakthrough ever since the GNSS technology has come onto the surveying field. This is basically a very accurate global positioning system, which is GPS, which many of your phones or Google Maps they use. They offer precise control and mapping, and specifically in Singapore, we use the RTK GNSS for centimeter level accuracy. When you combine GNSS with total stations, actually you get very accurate and precise results. So it's this kind of combination of technologies that modern surveyors achieve speed and reliability across large and quite complex work sites. Okay, I want to hand over the next section of the lecture to my colleague, Pei Cao, to continue with the lecture.
Okay, Thank you, Chen, for the introduction, and good afternoon, everyone. Um, I'm HR from Home Engineering. I'm the operation manager for the company. So I hope everyone have a brief idea about what is surveying, engineering survey, and what are the important elements that engineering survey needs to have. So the following 1.5 hours, I will briefly introduce the next few topics of the engineering survey, and we need to dive into detail about leveling today. So let's continue. An important element for engineering survey is angles. So what are angles? Hold on, maybe stop sharing. Let me show this. Okay, so all right. So you can see ancient time surveying equipment. Actually, the surveying you have two angles, horizontal and the vertical angles to consider. Horizontal angle is actually basically that when you turn from one point, which is the benchmark or station, to another point, the horizontal angle when you turn. All right, and the vertical angle will give you the elevation difference and when you check the level. So okay, here you can see you can see the celestial meridian. You can see in the left-hand side the drawing. Okay, the horizontal angle when you turn from, you always remember turn from north and go clockwise. And this angle, we call it azimuth. All right. And when you turn from the horizon up or down to the vertical, so this vertical level, we call it altitude. And the point that directly on top of the observer is called zenith. Okay, so the right-hand side drawing is actually telling you how do we get the coordinates and level from one point to the other. This is actually the basic concept and the principle which later on you will use in doing traversing and the setting out. Okay, so in the international standard, the angle is actually radian, but in UK, the survey instruments measure angles in degree, minutes, and the seconds. So as the instruments that you are going to use later on during the lab. Okay, precision. The precision actually depends on the quality of the instrument, a surveying instrument, and the accuracy is usually state in terms of seconds of degrees. For example, for a set length of 100 meter, the instrument usually have plus minus 20-second accuracy, and a linear error about 10 mm difference. But for plus or minus 1 second accuracy, the linear error is usually about 0.5 mm. The accuracy actually is required, depends on the type and the nature of the project. So for some, let's say the earthwork project, it doesn't really need so accurate because the level like 10 mm is not really affect a lot. But for some structural engineering, like a building project or bridge project, it may affect a lot. So the accuracy actually and the precision requirement will be more stringent. So when we're measuring angles, right, using the total station or equivalent instruments, firstly, we shoot one point, the target, which is understand as a station. Then you will have its coordinates. Then after that, you will turn horizontally first, then turn vertical to shoot another target or prism, which is point B in this drawing. All right, and the theta, you see the angle, the horizontal angle, theta azimuth. Okay, this is the azimuth that you will get from point A to point B. And when you change the angle, the vertical angle from point A to point B, that is telling you the altitude difference. Okay, so round of angles. The theodolite level and the center over point W. So the targets are leveled and centered over the point X, Y, and the Z. So usually the surveying task will be measure the angle from angle of X, W, Y, and the X, W, Z. So the two angles. Okay, this is actually a plan. Is a plan view. So by using this round of angles, it can eliminate most of the possible errors in the instruments. So you may have a question that what are the possible errors in the instrument? Okay, here are they. First, you can see three lines. Line VV, which is vertical, and KK, which KK and ZZ is horizontal. And the ZZ is going through the length of the total station. And the KK is supposed to be perpendicular to ZZ and the VV. So the sources of the errors, first one is a line of the side, which is ZZ, not perpendicular to tilting axis KK. All right, it means that the ZZ is already tilted, maybe due to damage or something happened to the instrument. And second is the tilting axis KK is not perpendicular to the vertical axis VV. It means the instrument itself got some problem, or when you do setting up, is not level. The instrument is not totally level. All right, and the third one is the vertical circle, which is the ZZ. When you rotate, the reading when this vertical circle, when you turns to the vertical turn to the top to point to the zenith, the reading is not zero. And the last one is the vertical axis VV is not truly vertical. So these are all these errors can affect the final readings. Okay, next is the distance. Okay, so from this picture, we can see a few different distance. So in engineering survey, three types of distance are used: slope distance, horizontal distance, and the vertical distance. For most of the instruments, like a total station, it will automatically measure the slot distance, which is L in the in this sketch. All right, from point A to point B, the direct distance. All right, then the horizontal distance and the vertical distance, which is D and the delta H in the picture, or you can say V. That's actually is calculated by the instruments or by yourself. So only the slot distance is measured. And to measure the distance, there are some measuring tapes in surveying, and the setting out is used. So you definitely you can find some 100-meter long measuring tape from the market, but usually most commonly used is a 30-meter measuring tape. And usually you can see they are made from steel or fiber or plastic, mounted on an open or encased frame, as shown below. Okay. Okay. Total station, like what Shen introduced just now. Total station is actually extensively used for mapping and setting out, and they can measure the angle and the distance. Here is the horizontal angle, vertical angle, and the slot distance simultaneously with a relative ease and high degree of precision. The total station that you are going to use later on during the lab will be Leica TS6 Plus and TS7, which are very advanced model of total station. They can measure a lot of things at the same time quite accurately, and they're very easy to operate. Total station are capable of performing a number of different survey tasks and associated calculations, and they can store relatively large amount of data with a SIM card, sorry, the storage card inside. So all the total station functions are accessed through a keyboard and a display panel. All right. So you can control it by keying the keyboard, and the information, the data will show on the display screen. So for you to take down the record down the readings. Okay. And the total station is centered and leveled like a light. The procedure actually is the same. The setting up procedure is the same as you set up the level theodolite. And the measuring procedure is also the same. So the accuracy of most of the total station vary from 1 second to 10 seconds. Okay, so these are some instruments, a total station. Of course, just now I think Shen also showed the TS06 that you are going to use, which is the ones more advanced version. Okay, so now let's come to leveling, which is the main topic for today. All right, which is also the simplest element in engineering survey. So when you do surveying, right, you need to use auto level. We call it automatic level, or someone even called dumpy level. So this is the instrument, a cross section of the instrument. So you can see from left-hand side to right-hand side. Left-hand side you have an object lens, all right, and then you come to focusing screw. Focusing screw is for you to adjust the focus to make the your sight sharp and can read the staff reading easily. And this foxing screw actually is to control the foxing lens. And behind, at your right-hand side, you have the diaphragm and the eyepiece. And on the eyepiece, the crosshair is actually printed on that and covered by some protection layers. And you can see the center line is called line of collimation. This is very important. It's supposed to be always horizontal, 100% horizontal. So no matter how do you turn your instrument, your leveling instrument, it should at the same level. That's the basis on leveling survey. All right. Okay. So this is a telescope that used in survey. You can see the crosshairs is actually etched on the reticle. Okay. And usually they have two small stadia hairs also marked on top and the bottom of the crosshair. This can be used to measure the approximate distance. Okay. So when we're doing survey, right, we need the two guys. So one looking at the leveling equipment, I mean the instrument, like auto level. The other will hold the staff at the point of the survey. So when they the guy who is holding the staff need to make sure that the staff is always vertical. All right. You cannot turn upwards or backwards. Otherwise, the reading will be affected. Of course, if you don't keep the staff horizontal or shift to left hand side or tilt to right hand side, the guy who is the surveyor who is watching the telescope will straight away tell you it's not straight, and that the reading cannot be read accurately. Okay, so this is one of the side of the level from the level that you can see. So how to read the level? After you adjust the focus, you can see very clear picture, but you may not know how to read, right? So firstly, the first step to establish the reading is that you see the number. You can see a big number 1.9, black color, right? So it should be somewhere around 1.9. And below 1.9, there is a red color line. So this line is actually 1.9 meter. And then on the right hand side, you can see marking like a number 3, but actually is a grid. All right, each grid stands for 10 mm. Okay, so please remember, you see the bottom of this 3 is in line with the red color line below 1.9. So 1.9, so you see the bottom line is 1.900. And when you jump one grid is 1.910 because it's 10 mm. Then you jump again, another 10 mm is 1.92 mm. And when you go to the middle of this, number 3 is 1.930 mm. But your crosshair stop at somewhere above 1.930 mm. So here you need to estimate whether it is at the middle of the two grid in between. If it is straight away at the middle, then it means 5 mm, but it is not. So it's between the middle and the bottom. So it's somewhere either 1.932 or 1.933. Okay, it doesn't really matter because it's only 1 mm difference. even in the real world survey, there are some such error. Later on, we can do correction. So based on your own justification, you can say is about 2 mm up than 1.930. So that's how you get 1.932. Okay, so let's continue. Okay, then what is leveling? Leveling is actually a process to measure the level, the elevation difference between 2 points or more points. All right, and usually like what I introduced just now, we use auto level, some like what Shen already introduced. You can also use digital or laser levels, depends on the situation and needs. And the level line and the horizontal line. Okay, so one important definition that we need to understand is a datum. So this datum is nothing but a reference surface or line to which the elevation of point is referred. So all the surveying systems need to have a datum. And in Singapore, we have the Singapore height datum, SHD, which is also the mean sea level and is defined as 0 meter. Okay. Another element, important element that we need to have is benchmark. Usually we call it a TBM, is a temporary benchmark or permanent benchmark. This benchmark is to make the data accessible to all the users, surveyors. All right. It's actually reference to the datum also, and they have their own levels marked on the ground. All right. So when you do survey, you can when you get this benchmark, you can straight away tell, oh, what is the reduced level of that benchmark. All right, is a known point. Okay, so this is a sketch of how do you do a leveling. So you can see 3 points, A, B, and the C along the whole sketch. And on the left hand side, you can see a tripod with a level, auto level, and the red color vertical one is the star. All right. So the first step is that you just assume this A is a benchmark. All right. You know its level, and you put the stuff on A. Then you get a reading of the elevation by using looking through the telescope. All right. And this what we call is backside. All right. The backside is always your first reading on a known point. Okay, means the level of this point is already known. Then you read this point first, and this reading is called backside. Okay. And then you shift your level, your staff to point B, and then you turn your auto level towards point B also. And then you get another reading. This one we call it foresight. The foresight means is the last reading before you shift your level instrument. Okay, remember I repeat, this one important. Foresight means your last reading before you shift your level instrument. Okay, because later on you will see there are some intermediate readings and intermediate sites. That one we don't count as the last. Only the last is called foresight. Okay. Okay, then after you read the foresight, then you move the instrument to another point. Of course, after you shift your instrument, you still need to do the backside to point B, because in the first round of surveying, you already get the reading and the level of point B. So this point B is known point, not as of now. So you backside to this point, then you repeat you can repeat the procedure like what we introduced just now. And here, an important concept is change point. So this point B is a change point. Why is a change point? Because after this point, you change the position of the instrument. Okay, so when you read, after you change your position of your level, always point to the change point and get your backside reading. Okay, then after that, you can shift your staff to point C, then get your foresight reading on the staff. So then you can get the final level of point C. Okay, so here I would like to introduce a rise and fall method, how to calculate the point C level from point A. So like what we introduced just now, point A is the benchmark. The reduced level you already know. And then you shift to point B. So point B give you a foresight, the first foresight. All right. Then later on, you change your instrument direction, instrument position. Then you read the point B again, you get another level, which is the second backside. And then you turn to the point C, then you get the foresight. So you see below the table, the first three columns is for you to record down the backside reading, intermediate side reading, and foresight reading. Here in the drawing, in the sketch, we didn't show any intermediate reading, but we just assume in between A and B, there are some other points that you're also taking survey. So if there is, these are called intermediate points, and the readings will be intermediate site reading. You can just record down. Okay, then the point B reading will be foresight reading. And remember, how do we do for rise and fall? How do we record rise and fall? So the rise and the fall means the second point to the original, it means your foresight or intermediate side compared to the backside, whether it's higher or lower. All right. So you use your backside reading minus your intermediate side reading or your foresight reading. If you get a negative reading, you get a negative value, it means fall. Why? Because in this picture, you can see A is higher, B is lower, right? So the reading from A, your backside reading from A is shorter than your reading at the point B. So when you use a smaller one, smaller value minus the bigger value, of course, you will get a negative value. So this negative value shows that, oh, B is lower than A, means B is falling from A. And if in another case, from B to C, if you compare the reading at B and the reading at C, B is longer, C is shorter, right? So if you use the backside, you taken from B minus the reading you get from C, you will get a positive value. And this positive level will tell you that it is the C is rising from B, means higher than B. Okay, so if you don't remember or if you messed up, which is fall, which is rise, plus is fall, minus is rise, or you cannot remember clearly, you just remember this theory. All right. This drawing, it will tells you what is fall, what is rise. Okay, so now let me have a brief summary of the leveling procedure. So first, when the auto level has been set up, you always need to start with a backside on a known point, which is a benchmark. All right, and the last reading at any instrument position is always the foresight, and whatever in between is the intermediate site. Okay, then every time either you only move the staff or only move the instruments. Don't move both together. Otherwise, you won't have a change point and you cannot transfer the levels correctly. Okay, and the last principle, you always need to finish the leveling on a known point, another benchmark in this case. All right, to close your leveling. Why? Because you need to check whether you have any error or not. If you go back to previous, if you still remember how to read the stuff, as what I mentioned, there are always some different interpretation, whether it's 2 mm or 3 mm. So that's can contribute some errors, and also the instruments may contribute some errors. So when you transfer a few points, the error may be bigger and bigger. So that's why you need to always check back with another benchmark to counter check whether your readings are correct or not. Is that accurate or not? So here I will show you an example. Okay, so in this layout, you can see two stars, right? Left-hand side and the right-hand side. These two stars are the benchmarks, okay? TBM, temporary benchmarks. And the green color line stands for foresight, and the pink color is backside. So do remember that we always start from backside, okay? And then do the foresight. So, okay, we practice using rise and fall method for leveling. Okay, so you can see the first benchmark at the left top corner. We already know the level as 1.546. Okay, so you put your level on a point that you can both see the star, which is the first TBM, and another change point. Okay, then you backside you read 1.546, and your foresight it gives you 1.562. So you write down your two readings, one at the backside 1.546 and the foresight at the 1.562. All right, then you shift your instrument to the next level position. Okay, at the left down left bottom corner. Okay, then you read back to the first changing point, which is 1.416. Okay, that's your backside. So you put down this number in the backside column. That's your second backside. And then you read, okay, so here you can see some cross, right? A plus sign. These three plus sign are the, use pointer. Okay, so these three these three are intermediate sites that some points that you also need to take levels. Okay, after you take the levels, the readings you put at the intermediate site. Okay, one by one. All right. Then lastly, you read your false site. Here is another change point, and the reading is a 1.321. So you write down at the false site column, and then you keep the stuff there. You change your level again to the third position. Then you read your backside first. Backside. Okay. Then the reading become, the new reading become 1.011. And your foresight reading gives you 2.007. So you record down accordingly. Okay. So now level taking all completed. But how can we get the reduced levels of each point? By using the rise and fall method. First thing, you use your backside, first backside minus the first foresight. It gives you a minus 0.016. So if it is minus, right, it is 4 because it's lower, right? And then you use this known reduced wet level. Let's assume it's 10, okay, 10 meter. Minus, if it is 4, then you need to minus, okay? Minus 0.016, then you get 9.984. So that is the reduced level, calculated reduced level of the first change point. So subsequently, you repeat the process. You use 1.418 minus 1.390. You get plus 0.028. That means rise. Okay. So you record here. Repeat. Then from 9.984, you plus this 0.028, you get 10.012. So that's the reduced level for the first intermediate site. Follow the same schedule. You do the same calculation, then you can get the second intermediate point reduced level and the third one. Okay. Lastly, from the intermediate to the foresight means this point to here, okay, the readings, you use this minus this is minus 3.741, okay, is 4. Then you need to use this reduced level minus this one, you get the 10.081. That's the second change point reduced level. So you follow the same procedure. In the end, you can get your last point calculated, surveyed level by a calculation, 9.085. Okay. But okay, like as what I say, the surveying always need to close, means go back to the benchmark. And this benchmark, the level, in fact, we know is actually 9.09. All right. So this is how do we check whether there is an error or not. By our own survey and calculation, we get 9.085, but the benchmark level is 9.09. So there are 5 mm difference. Okay. So there is an error. The error is a 5 mm. But is that acceptable? Is that acceptable error? Okay. How to check whether it is acceptable. There is a rule of thumb. Okay, the allowable misclosure is plus minus 5 times square root of n. And this n is nothing but the number of the instrument positions that you made during the surveying procedure. Okay, in this case, we change the instrument 3 times, right? So they have 3 level positions. Then this n is 3. So 5 times a square root of 3 is plus minus 8.66, or we say maybe 9 mm. And our error is only 5 mm. So it means that it's acceptable. All right. Otherwise, if let's say the error is more, let's say 10 mm, more than 9 mm, then you may need to go back and do the survey again because the error is not acceptable. Okay. So we already calculate the error is 5 mm. Then how should we do the adjustment of our readings? So we have 3 positions, right? And these 5 mm should actually happen during the process gradually. That's most possible scenario, right? So if let's say if this occurred gradually, then we can actually distribute them evenly. Let's say we use 5 divided by 3, but if 5 divided by 3 is actually 1.667 something, and you cannot just adjust each reading exactly by 1.6667 because after 1 mm is not really recognized and is not really meaningful. So in this case, we can adjust either 2 mm or 1 mm on each point. Okay, there are 3 combinations. 3 different combinations to distribute this 5 mm among the 3 positions. All right, either the first point we put 1 mm, and the second position we put 2 mm, and the third we put 2 mm, or the first is 2, second is 1, and the third is 2, or another way is 2 to 1. All right, so in this case, maybe either one is okay. Actually, is the same as long as you get the final reading correct. And like what I say, 1 mm for the reading is actually acceptable. So in this example, we take the second distribution method. Okay, so at the first position, we add 2 mm back to the reduced level that we calculated. And for the second position, we add another 1 mm, means 2 plus 1 is 3 mm, okay, for the second position readings. And at the last position, we put another 2 mm, which means the 5 mm error back to the readings. So this is this column is the field calculation, and after correction, you get the corrected level, reduced level, and this one should be the final level that you can conclude for all the points that you surveyed. Okay, so the rise and fall method help you to check whether your calculation is correct or not. There is a formula. You always remember that the sum of your backside readings minus your sum of your four-side readings always equals to the sum of the rise minus the sum of the fall. It also equals to the last reduced level that you calculated minus your first reduced level. Okay, and then when you check the misclosure, which is the error, the rule of thumb you need to remember is plus minus 5 times square root of n/mm. Okay. So now let's do practice. So in this sketch, you have a few points A, B, C, D, E, and you have two benchmark TBM1 and the TBM2. Okay, and below is a plan. So and you have total 3 different instrument position, which is I1, 2, and 3. So the process is always you set up at your level at the L1, all right? Read the benchmark first as your backside, okay? And here is your reading. And then you read your intermediate points, then you get the intermediate side at A as this 2.505, and then B, and then C. C will be your foresight because this is the last point that you read. Okay. So this C will be a change point. Then after that, you shift your level and you read backside on C first. Then intermediate point D, and then your foresight E towards E, right? And this E is another change point. Then you change the position of your level again. Then you get another reading on E as your backside. And finally, you close your leveling on TBM2 and you get another reading. So here, as what I mentioned, what is the backside, what is intermediate side, and what is the foresight. Okay, so this is just for your reference. And they tell you the TBM level. TBM1, the level is 49.873. So now we use our rise and fall method to do our booking. Okay, at the I1 position, the foresight on TBM1 is 2.191. Okay, all these readings you can find from this sketch. Okay, so then you just record down on your booking these 3 columns, fill in, right? Then you do calculation. Backside minus the foresight, then you get minus, then you put on 4, right? 0.314. And then you use this intermediate side minus this intermediate side, you got a plus 0.18. Then it's rise. All right, then you fill in the rise. So after that, you repeat this. You calculate all the rise and the fall. And then you calculate the reduced level by using, okay, this is a benchmark, this is a given level. Then you minus this 0.314, you get the reduced level. Then you repeat the procedure, plus or minus, then you can get the reduced level of all the points. And then this is a calculated level on benchmark 2. Okay, so before we conclude, we do arithmetic check by using this backside, foresight sum calculation. Okay, so the backside, all you add up together, you get this 6.962. And all the foresight reading, you add up together, you can get 8.131. So use, okay, here you use 6.962 minus 8.131, you get minus 1.169. All right, and the next step, you check the rises and falls. Rises, you add up together, you get this 1.515. Falls, you add up together, you get 2.684. Then you use 1.515 minus 2.684, you get minus 1.169. Okay. Lastly, you use your last reduced level, which is 48.704 minus your first reduced level, 49.873. You get the same number. So you compare these three numbers, all should be equal to each other. All right. If it is not, means your calculation got something wrong. You need to recheck. All right. Okay, after checking, nothing wrong in calculation. Then you can tell how good is your leveling, right? So for any lines of level, you must check back to the original TBM or another TBM to close your leveling. Otherwise, you have no way to know your accuracy of your work or if there's any error. All right. For most of the construction work, the allowable misclosure is given by plus minus m times square root of n. M is the constant. In this case, is 5. And n is the number of instrument positions during your leveling survey. So in the industry, right, for earthwork means excavation, backfilling, or some other hacking or whatever. So it's called earthwork. All right. In earthwork, I also mentioned M can be a big number as 30 mm because it's not so significant if the error is within the 30 mm. But for if you want to setting out for a concrete or steel for some structure, then M can be even as small as 3 mm because they want quite precise. If let's say the error is too big, then later on, when you want to further build up your structure on top, or you want to connect the steel beam or column, it cannot align to the holes of the nails or the screw. Okay. So in this example, we use 5. It's in between. It's slightly more than 3 mm, but it's also quite a high standard. Okay. So the source of errors in leveling, it can comes from the equipment, means the instrument, or from the field. So errors in the instrument is usually the collimation error, means it's not straight, it's not horizontal purely, or the compensator doesn't work, or is also due to some parallax, or the staff also got some defect. So the reading is not accurate, or the tripod may have some defects, so it affects the instrument. Some fields error will be the staff is not vertical, is not handling vertically, so it affect the reading accuracy, and also the poor choice of change points, which after you change, you want to look back to the change points. It is not easy to see, or is a bit blur, or you can see half or what. Then you need to adjust your change point. Okay. And the last will be reading and the booking error. Means when you read, it's supposed to be 1.93, but you read as a 1.94 or 1.97 or something. So this kind of a reading error, or when you record down, you get the reading correct is 1.93, But when you write a 1.94. So all these can make the final reading wrong. All right. Okay. So some of you may ask, what is parallax? Which is one of the instrument error. So this parallax is okay. All the leveling instruments have a crosshair, and this is the parallax error is actually affected by the optical. And how to check whether have this parallax is quite easy. If you, before you do the leveling survey, you can move your eye in front of the eyepiece, up or down or left to right. Then you see the reticle. Is that moving when you move your eyes? All right. If it moves, then means the parallax is not good. All right. So every time before you start measuring, checking the parallax, every time before you start do survey, you do check your parallax, and the procedure is like you aim the telescope at a high contrast or bright background, all right, to make your sight very sharp and clear. And then you focus the crosshair by turning the eyepiece drive. And lastly, you focus on the staff or the prism. Okay. Okay. One more way to double check whether your instrument got any error, especially on compensator or your collimation. Okay, in the level instruments, the compensator has been adjusted at the room temperature, so that the line of the sight is always horizontal. Even the instrument is tilted a bit, all right? But if the temperature change a lot, then it may affect the sight inside your telescope. All right. Usually, if the temperature change more than 10 or 15 degrees, then after a long journey, or if the instrument is subject to excessive vibrations, then the compensator maybe need to adjust again. So how to check this error? The procedure, you got totally six steps to check. First of all, you choose a flat ground. Okay, then you set up two staff, like not more than 30 meters away from each other. Okay, then you set up the instrument in between. So at the center, right? So then you can read the two staff. And later on, after you read the staff, you record down. So the staff reading at A, you got 1.5. You got this 1.549, and at the staff reading B, you got 1.404. Okay, then the delta H means the difference. The level difference is 0.145. Okay, then you shift the instrument to nearer to 1 point, let's say 0.8. Okay, then you get another reading, like 1.496. Then you calculate the reading of B by using the new reading from A, 1.496, minus the previous difference, 0.145. Then the required reading IB is supposed to be 1.351 if the instrument is no error, is working well, all right, the condition is good, then you read. So if your reading is within 3 mm, then it's acceptable. But if not, that means the instrument got something wrong. We need to adjust it, right? So this is the test to test the instrument. It's quite important before you use it. So please remember this. All right. Okay. So this spreadsheet is the level reduction spreadsheet, which is also the rise and fall method. It's following the rise and fall method. It's quite important. Please remember using this. Later on during the lab, we need to use this spreadsheet. Okay. And this table can guide you, this spreadsheet can guide you to do the calculation of rise and fall and eventually get your reduced level of your survey points. Okay. And this is another one. All right. So it's quite important. Rise and fall spreadsheet. Okay, you can develop your own one if you have your survey leveling and the stuff. You can later on when you do the lab, you can try to use this. Okay, so that's all for the leveling. Yeah, for the leveling lecture. I will end the lecture today here. Do we have any Q&A session before we jump to the lab? Oh, okay. So I think we still have some time. Maybe I can use this time to brief you about the first lab, which will happen on next Thursday and Friday for different groups. Then I show my. I will share my watch. Oh, you stop sharing. I gave you the pause. Okay. Oh yeah. Okay. Sorry. I hope everybody can see my screen. Okay, so first lab is a practice on leveling. First of all, I need to remind everybody on the day on next week, Thursday and Friday, when you attend the lab, please wear long pants and covered shoes. It is for your safety. And if the weather is hot, bring your own water bottle and drink enough water. Because it may take some time, and someone may need to stand on hot sun for a while. Okay, equipment needed for leveling. We need a tripod. Okay, this is a tripod. Oh. Point. So this is a tripod. And the screw, the tripod head and the screw. So this screw is actually to fix auto level. And before we use it, we need to adjust the level of auto level. All right. So how to adjust the level? First of all, you will see a bubble on the instrument. Always turn the two screw under the level instrument on a different direction. Okay, your right hand side, you turn to the following the clockwise direction, and your left hand side turn towards the anti-clockwise until the bubble shift to the center. All right, shift to the center line. All right, center line of your tripod, or in between A and B. Okay, then after that, you only adjust the screw C to make the bubble go to the center. All right, that's the easiest way. But this is called fine leveling. Actually, you have a coarse leveling means adjust the tripod first. All right, adjust the height of the each leg to make it almost level. Then it's easier for you to adjust. Otherwise, if your tripod head is not in level, then no matter how do you adjust the screw, the bubble may not go into the center. All right, and the last equipment you need is the staff to read the level. Okay. Modern instrument. This actually is a total station or electronic total light. But they are not really using purely leveling survey. They are more on traversing, mapping, and the setting out or monitoring. You still can use it, but if you are only taking level, better use auto level. It's simpler, it's easier. All right. So like what I say, you set up the theodolite, the or level or whatever instrument. So firstly, you need to center and level the tripod by using your eye over the survey point, and then you should place the instrument fully on top. So make sure the screw, the tripod screw, fully tightened with the instrument. Otherwise, it may drop down. It slide or drop down. But don't over tighten also. Okay, especially the tripod. Let me go back. Okay, if you see right, actually the tripod here got a thumb screw. For you to turn. It's actually to fix the tripod leg, but don't overturn because these are all aluminum. If you overturn, it will damage the screw. Okay, and the leg will be damaged later on. Either it cannot secure, or the tripod will be deflected. It will be further damaged. So try to tighten it, but don't overturn. Okay. So this is what I say. First of all, you need to check you need to center the instrument with the point. But this is more on for your traversing when you set up your total station. For leveling, you don't really need this because your instrument can put your level instrument can put anywhere, right? As long as you can see the staff, you can see your backside and your change point. Okay. This is how do you adjust your level. All right. As what I mentioned, you first of all adjust the two screw at the same time to make the bubble go to these seats. Then adjust the last one to make it to the center. Okay. So then you turn the instrument and check whether the level is at the center. If not, then need to do some minor adjustment again. until when you turn a few rounds, the bubble is always at the center. Then you can confirm, okay, the instrument is fully level at the horizontal already. Okay, reading stuff. This one we already covered during the lecture. Remember, the staff must be vertical. Okay, don't tilt up front or back or left to right. It will all affect the readings. Okay, so this is a practice. So reading, first read the black color. That gives you the first two numbers. And then from the red line, you see how many grid you have. This is the first grid, second grid, third grid. So means 1.11, 1.12, and 1.13 here. Okay, so it's slightly above 1.13. Either you say it's 2 mm or 3 mm, it doesn't really matter, but looks like it's closer to, here is 1015, and if at the center is 1.135, right? So it's slightly under the middle at the center, but it's closer to the center. So we put it 1.133. All right, so this is the method. Okay, then when you next week when you go to site, we have different loops. With this loop, this is actually one of the loop, loop 4. You can see the stations on site. You can start from station 14 as an example here, and we assume the reduced level is 100. Then you will put, okay, you can put your position of your tripod in between station 14 and 15. Then you read your backside at 14. Then you track your foresight on 15. All right, so you take down backside and foresight. Then again, later on, you change your tripod to another position. Then the station 15 become your change point. Then you read your backside, your foresight, and record down. Then again, you change your tripod position to position 3. Then read back station 15, then foresight, station 13. Lastly, goes back. Okay, goes back to station 14. Remember, we always need to close our surveying by to a known benchmark. All right, so you read your backside, your foresight. Then you use your rise and fall method to calculate your reduced levels. All right, so this is a spreadsheet. Okay, then after you record down your backside, your foresight, you list down. Okay, then you can calculate your rise and fall. Then from there you can calculate your reduced level. Remark, you can put the station number or any intermediate points here. Then you can do the next step is what? Is checking. All right, checking your backside sum of foresight, sum of rises, sum of falls, and then you use your backside sum minus the foresight sum, you get one number. Your sum of rises minus falls, you get the second number. Then you use your last reduced level minus your first reduced level, you get the last number. Then you compare these three number whether they are same. If they are same, then you can proceed further to do your misclosure adjustment. All right. Okay. So these two, the first two column, foresight and backside, is the measured data from the field activities. The middle part, rises and the falls, And also the reduced level is your calculation part. Okay, the last remark column is the station info. Okay, remember this. Okay, so this is our surveying loop and the point. We have, like as what I mentioned, we have 4 loops. Loop 1 is in between our block E2, E and E6. All right. And loop 2 is also from E2 to part of E6. And I think here is E1, right? And loop 3 is in front of E6. And loop 4, which I took as an example, is between E4 and the E5 and partially at the E2. Okay. And each group, okay, will have one level, one pod, and 2 staff. In fact, actually, each group, right, we will have 2 groups, and each group, I think, yeah, each group will have like 4 or 5 students. So it means that probably one group, like 1 staff is enough. Means you have 1 level here, then 2 students follow level, 2 students for holding staff. Then another team, another group 2 will stand here with another staff. So then after that, when you shift to the next point, I think you can change. You can internally change. Someone, the first round you already hold staff. Then the next point you can do reading through the level. Okay. Then the third point you change again. So we have each loop we have 4 points. So it means that each student have a chance to use to both handle the stuff and read the level. Okay, sure, you have the chance to experience this. All right. So okay. There are some requirements of this leveling lab. All right. Each group is required to submit a technical report justifying what you have measured and calculated during the lab session. And the report should include at least your group member's name and student's ID and their role. So I hope actually your role, either surveyor or staff chairman, I think both roles you will practice. Or if you want to mention like a group leader, it also okay, right? Who is the group leader? Okay, I think that's also an important role for the group. And then also the information. You need to describe your objectives, what equipment you use, and the study area. You include some photo and the sketches. So like say, if you survey loop 1, you should have at least your sketch of your loop 1 sketch. Okay, and the methodology, which should be captured in the body section of the report. Need to provide your measured data and your calculations, and the station information with the pieces of evidence. For example, your booking sheet, your raw data, and your calculation procedures. And also, how do you check if there's any error during the calculation? Okay, and also you check whether there is any misclosure. All this you need to be captured in the body section. Then the last part will be your conclusion. All right, to present the calculation and the recommendations. Like, okay, we already checked there are some, the calculation is correct. The misclosure is how many whether it is acceptable, why it is acceptable or not acceptable. Okay, if it is acceptable, then what is your adjustment of your readings with the misclosure errors? All right. So the assignment will begin on week 9. The deadline will refer to your Dropbox. Okay. I think, lastly, I think we still have a little bit more time at that script. I will show you some videos for your information how to do leveling. Oh. Can everybody hear the video sound? Please do. Maximum warning. Just to be clear. But allow me. Sure. Can you hear the sound? Oh. Oh, you would. Mm. Okay.